Welcome to our final session for today. We're going to see a bunch more really cool examples of data science and applications into various areas. And our first speaker is Claudia Perlich, who's the chief scientist at Dstillery. And she has lots of experience in data analytics, data mining, machine learning for various applications. And her PhD is in information systems from NYU. And let's all welcome Claudia.
It has actually been a great pleasure to be here. And it's kind of looking at this whole Dstillery, back then named Media 6 Degrees, and since then I've been working in display advertising, which I find to be a real fun playground to play around with data and figure out what works and what doesn't. So that's what it's going to be my talk today, is about things I do at Dstillery. And if you are one of the 200 million browsers like my mom who hasn't figured out yet how to switch off these pesky third-party cookies, then we might actually be collecting information on you. So when she's browsing the internet and is reading blogs or just visiting various sites, we may have a data partnership that allows us to put a cookie on your computer at that moment. So it's a pixel on the side that gives me the right to store some small information on your computer. And all I'm going to do with that, I basically just assign you a 20-digit random number. That's all that this cookie is going to contain. Now, how's the company making money? We would work with marketers and brands, and they want us to run display campaigns with them. Now, Dstillery actually has acquired also some mobile arms, so I'm only going to talk about the display side of things. What we're going to do for these display campaigns, we'll have a pixel put up on that brand's homepage and checkout page as well. So now we're going to see who is going to buy the product that the company wants us to advertise to on their homepage, or who's just going to that site. How do we make money? What is the actual service we provide? As people continue browsing, they may get to a site that has a slot for display advertising. And more and more so, a large percentage of these slots are sold programmatically, which just means that there is a real-time auction while the page loads, where the opportunity to show you an ad is sold off to the highest bidder, and there are plenty of us, through an advertising exchange. We get about 10 billion bid requests every day, and for each of them, we have about 30 milliseconds to make up our mind whether we actually want to show an ad at this point to the person. The key piece here is, I again know that it's the same 20-digit ID that I gave you earlier. So there is some kind of syncing. I know who the person is, not who you are, but you're the same who that you used to be when I saw you before. If we win, we get the opportunity to show an ad, and then we're not going to be interested in predicting clicks, which we had earlier in the Google talk come up, but we will track then over the next 7 days whether or not the person who saw the ad goes to that brand's homepage and actually buys the product. That's what we are going to call a view-through conversion. Now, I said it's a great playground. There are many, many interesting problems here that you can work on. The primary one that I'm going to spend most of my time on is the main decision I have to make is who should I target? Who should I show an ad for, say, running shoes? The next question is, what opportunity is a good one to show you that ad? Meaning, what price should I bid, and on what site, when you're currently reading, would be appropriate? There is the question whether ads actually matter. Occasionally, we do ask ourselves whether ads matter. I'll talk a little bit about this. It's actually quite surprising how few marketers want to know the answer if it's the truth. So we have to pay for our data. One of the questions I need to answer on a regular basis is, what is the value of data? So in this kind of big data where everybody collects everything, I have to pay for it. So I have to think twice whether it's worth it for me to acquire a given data set to augment the information I can get. And then there is the problem around attribution, which has actually some interesting academic contributions as well. They go into game theory. Who should you credit? Because if it's not the click, but the 7-day view through, when you buy the product, you have not just seen my ad, you've seen hundreds of ads. And not even talking about billboards here that I don't know about. So who will get the credit from the market's perspective? That's called attribution. Finally, and there's not by accident that the ad exchange is a black cloud. As all trading exchanges, it opens itself up to fraudulent behavior where people try to skim the system. So there's a lot of interest right now in fraud. So that has become recently another area of investigation. Now let's look at the core problem. If I need to decide for 10 billion bit requests a day, what is the value I want to assign to the opportunity of showing that person an ad at that point in time on that inventory? In terms of the space, what we are collecting about people are URL histories, the places they have been to. We have roughly floating about 100 million of those in our system. We run, on average, 300 concurrent campaigns. And we have officially classified about 15,000 inventories, meaning places where we can show ads. In terms of the dimensionality of the problem that I'm posing to you, there's just no way to solve this. You can't just throw it in the automated machine learning system, even if you figure out how to set these pesky learning rates automatically. That isn't the problem. The problem is it's just set up far too wide. You need to think about this. Now, all of this really is, when I talk about these probabilities here, I think most of you are aware this is predictive modeling. It's a classic instance of estimating conditional probabilities. Most of what I'm going to talk about is how do I use data that are labeled to estimate equations with many, many parameters. Our primary workhorse is logistic regression. I'll talk a little bit in details about that. So everything I do, this is kind of what they pay me for, core competence is building these machines that automatically learn models where you estimate betas to then be able to predict something. Now, what is the golden rule? If you study machine learning and predictive modeling specifically, what are they going to tell you? Well, there is this, the statisticians will tell you it has to be IID, right? The test sets to be IID, meaning you should have the data where you want to use the model for supposed to be as close as possible as the data you have to estimate it. That means it should be the same sample, and things should mean the same thing, like labels. And you should optimize the right thing. If you want a very accurate model, then you have to optimize accuracy. If you want a good ranking model, then accuracy doesn't really matter at all. And the second footnote is you need to have enough data to do so. Otherwise, you have to maybe simplify your model or think about this. And thinking about the theme of today's conference on weathering the data storm, for me, the irony of big data is, so now we are in the time and age of big data, and I can get data on almost anything, and I still don't get enough of the right data that I need to solve my problem. And I'm arguing that there are a lot of problems out there that still fit that. So what do I mean by right? Well, if you really believe that this is my problem, I want to predict the probability of somebody buying the product, given what I know about the browser and the inventory and the ad, well, this is just the label, right? This is the dependent variable here. Now, these things will become features, and the fact that I've shown you an ad is kind of a conditioning on the sample. If I wanted to collect the correct training set to build this model, what I need to do, I need to find me a whole lot of random people, show all of them ads in all kinds of places, sit and wait for, say, 7 days, and see who then actually goes and buys running shoes. If I proposed that to my CEO, I wouldn't hold on to my position for very long. So I cannot get the data that I'm supposed to model, that I'm supposed to predict. Now, a little bit about the data I have to give you a flavor here, and that's interesting in terms of the representation. We're basically collecting very agnostic level. We're going to take the URLs that you go to, and we hash them. So I'm not going to crawl the whole web to figure out what's there. I'm not going to look at the content of the URLs. I'm just taking the URL, and I hash it. And then I gain from that kind of a browsing history that's just a date with this kind of hashed thingy that was a unique URL. On the other side, I know who bought what that I'm going to use as my target variable for building models. So in an abstract sense, and we had a lot of discussion about understanding and communicating, I have no interest in understanding what you're doing. I don't want to know. I don't want to know who you are. I don't want to know where you live or your age. I'm just going to hash all the information and I associate it with a random identifier that just helps me re-identify this same abstract identity that you have. Now, if you think about this now, how much data do I need? If I have 10 million binary URL indicators, and I'm now pretending to be a statistician, which I'm not, who I vaguely remember told me that N over P should at least be 10, I'm in trouble. Because I need an order of magnitude more than 100 million examples. And by the way, it's not the examples that I need, because I need to classify things. So first of all, at the beginning of the campaign, I have exactly 0 examples, because I haven't shown any ad yet for that product. So I have absolutely nothing. I have plenty of people. But that sample, I have nothing. The other problem is, coming back to the N over P, it doesn't really matter what N is. What matters is how many people do I observe buying stuff. And believe it or not, there are very few people who buy luxury cars online. So conversion rates are typically extremely low. So what are we going to do about that? We're going to cheat. Now, that's the good news. In machine learning, this is called transfer learning. A couple of tricks. Let's start. First of all, I'm going to make a whole lot of small problems out of that one big problem. Statistical terms, I assume independence all over the place. And I'll talk about a few of them separately. Let's start with the big problem of targeting. So what do I really want to estimate? I want to estimate the probability of buying given the URL history and the inventory and the ad. I mean, who of you believes that ads that you see actually influence your shopping behavior? Not too many. Good. So you all agree that we can drop the whole conditioning on the ads and inventory. So forget it. Let's just not deal with it. Let's just ask, can I predict who would buy the stuff anyway? So that's the organic. Now, the second part is, I'm going to change the target variable, but let me get there in a moment. So basically, the first is I'm going to bias and change the problem. I'm not going to show people ads. I don't even care about that. I will change the target variable from actually buying to just going to the brand's website. And I'm not going to sample very well. I'm just going to take everybody I've seen purchasing. And then I find myself a couple of people who didn't. I mean, I have a lot of those, right? So in terms of sampling, the one thing you never, ever want to do in predictive modeling is pull your positives from a separate place than your negatives. That's always asking for trouble. Well, but here I am. I'll find a very, very simple model class. So linear models, naive Bayes, logistic regression. I do a little bit of hand-holding on the URLs. Here's why I can't do feature selection. Even for feature selection, you need some labels. And if you don't, then you kind of generic dimensionality reduction, which we tried, doesn't work very well. Finally, I don't want to build a different feature space for every marketer. I don't have time for that, talking of taking the person out of the loop. I mean, we are 5 people. We are building models for 300 marketers, roughly 10,000 of these models a week. I can't do the grad student descent. I love that, by the way. So they all have to kind of work the same way. Here's the first observation on the target variable. All right. if purchases of luxury cars online is so rare, what else could I use to predict? Well, you can try to predict clicks on ads. Turns out, and we estimated this over a large group of campaigns here, if you build models on clicks and then evaluate how well they rank purchases, they're exactly as good as random. So you may as well not bother. Now, the footnote here is this is true for generic display advertising. That's not true for search or for some of the other ones, but in generic display advertising, if you optimize, if you evaluate, if you just look at the click-through rate, and this is after filtering out all the clicks from China and various other things. So there is no signal, there's no correlation. Because basically all you get is people who have eyesight problems, but aren't interested in the product. Now, if you optimize towards purchase, you do better than random, predicting purchase. What's really interesting is that optimizing against site visits, whether or not they bought, is irrelevant. You are better at predicting purchases. And that's an example of transfer learning in some sense, because I completely changed the problem. I take a different target variable, and it works because I'm navigating that kind of bias variance. I'm biasing my model because I'm asking it a different question. But because I get so many more positives, I can reduce the variance of the estimator and still end up getting a better model for what I really want to predict, which is purchase. So let's move on. And now the question is, how can you predict site visits based on a large dimensionality of URLs? First thing, we're going to use stochastic gradient descent, logistic regression. We'll put in a couple of constraints to further reduce the variance. That should sound familiar given the last talk, so I don't have to talk about this. All these learning rates and hyperparameters, we're not nearly as sophisticated as Ryan's presentation, but still. We use Bayesian priors for the parameters as starting points. So maybe I don't know about running shoes, but if I know about footwear, maybe that's a good place to start a model. We built them streaming, so they kind of constantly update. So there's a current model, and it gets just refreshed based on the last hour's data. That goes on continuously. And all of that's completely automated. Nobody's looking at this other than looking at some kind of QA emails once in a while that come back. And we build roughly 10,000 of these models with slightly different settings per week. Now, here's a problem. If you look at the performance of that model, and on the right, you see something that's related to a calibration plot. So I'm showing how well the model predicts in terms of ranking, comparing the predicted probability that is scaled against the observed. It looks like we pick up something. In the ideal world, this should be an identity line if the scaling is correct. But what you do see, and that's the red thing, those people I predict the highest probability for are actually not converting very well. And the reason is, well, I messed pretty much everything up I could in the first model, right? I took the wrong sample, I have the wrong target, all of it is. So I need to fix that. And this is called stacking, and is one of the tricks in transfer learning. I'm going to build a second model that uses the prediction of the first one as features. But this time I take the right sample. I actually really take a random cohort, and I'm going to wait the 7 days to see whether within 7 days they convert. So in addition, there's a little bit of nonlinearity there. So if I want to stick with my guns and like logistic regression, I need to put in some quadratic terms and deal with that. The other nice thing about this, now the dimensionality is 50. So now I can get really fancy with the machine learning, and it can optimize interesting things using, for instance, SVMs and optimize rank directly or AUC. All right. At this point, what we have is I have a whole set of models that can predict the probability of somebody being interested in purchasing a product. Well, site visits, but believe me that purchase is correlated. Once you get high enough with that score, and we constantly update this, every time we have a touch point where we see a new piece of or new URL that you go to, if you get high enough, we'll say, okay, now we start to show you ads. You make it above the threshold for every campaign that's different. And if things go well, you might buy, and if things don't go well, or if you already bought, then we'll see this tapering off. Which brings me to the bidding problem. How am I going to optimize the bid price and evaluate an opportunity? So now I'm actually dealing with that inventory piece. All Obviously, it matters what you do right now. We see that if we have a travel campaign, it's much better to show the ad on kayak, conditional on knowing that you are interested in travel. So this is a marginal impact. So what I want to know here is, given that I already know how good a prospect you are, how can I evaluate just the placement of the ad? And what we're going to look at is here, I as the inventory, I'm going to compare every possible place, a specific place, over all possible places where I could have shown you the ad for the campaign. Now, it turns out you can get away not having to deal with the expectations and the integral at all in machine learning. That the nice thing is you just drop the feature from the estimator and you get kind of you lose the conditioning. It automatically integrates over the empirical distribution. So all we're going to do, we'll build two models that one predicts with the inventory as a feature and one without, and we take the ratio for that. At this point, we know that the site is maybe twice as good than average to show an ad for a specific campaign. So now we translate this into bid price, and we have different strategies. Some are kind of cutoff functions, say never bid on the bad stuff, only bid on the good stuff. Another one is just multiply the base bid price by that ratio, like a value calculation. The final piece here, or not the final, the almost final, is the fraud. This graph here shows you a network of websites. Every red dot is a host name. And there's a line between two of them. If I see more than 50% of browsers who go to one, also showing up on the other. So it's an indication of co-visitation. Okay? We think this is a very good indicator of fraud, so we use it to blacklist inventory and also ignore browsers who we see there. Here's a subset of that. The center is women's health space. Now, I would like to point out the very diverse interest of people who go to women's health space. They also like China on TV, wrestling news, and things I can't even read. There's no way that this traffic pattern, meaning the co-occurrence, is human behavior. That's the footprint of a bot generating artificial traffic. And the whole point is to sell ads. Now, no brand likes to have their ads gone to bots where nobody sees it anyway. So this is an effort that had made recently some news. Finally, I want to touch on A/B testing. As many companies who have a lot of data, it's certainly of interest to us. And once in a while, we do have campaigns coming to us and want to do an actual A/B test. There are a notable amount of practical problems with it. First of all, you have to pay basically for non-ads. So somebody has to foot the bill. And then there's a great paper by Kohavi pointing out all the things that can go wrong with A/B test, and he suggests A/B tests and various other things. So the basic one is you can only ask one question at a time. You basically have to set up the test to answer that one question you want to know. You can't go back and change your opinion, and you really didn't want to know whether it was the ad being red versus now you want to know whether it being green. So what we were interested in, can we use just observational data on our campaigns to estimate causal impact of ads? And there is a very interesting stream of literature. We hired somebody out of Berkeley on targeted maximum likelihood, kind of double robust estimators of causal impact in observational data. And it really comes down to being really thorough at accounting for all confounding that could obscure your results. And it starts out defining a causal graph, which is very kind of Bayesian inspired. This is not going to be looking at parameters in the logistic regression. Although statisticians continue to assert that they can interpret these things, I've never figured out what to do with it. So we're not going to look at the betas here, but instead we use prediction of models to say what is the expected conversion rate with the ad, which is predicted from the model, and what is the expected conversion rate without the ad. We define causal effect as the difference or the ratio between those two. Here are some example results of what we have observed. And you see that apparently occasionally ads do work, not always. These are two different campaigns. Both of them had both retargeting and prospecting. Retargeting is if you show ads to people who have already been to that product site. And conversion rates are always much higher. Now, if somebody tells me they can do that I'm going to have at least 2 questions. First of all, can you prove that it actually says that there's no effect and there shouldn't be an effect? So we run a test here where we measure the impact of a pizza ad on buying cell phones. That better be 0. If it's not, then something is wrong with what you're doing. So that's a great test for causal estimation. We also had the luxury of actually running an A/B test. So we were actually showing public service announcements on a random trial. And then we ran the methodology of observational estimation 2 weeks later on the same campaign. And I was blown away how close these 2 things got. So that's some evidence to me that we do have occasionally the chance to just use observational data and back out causal inference. So as my time goes to the end, I want to take the opportunity, and Hans-Peter knows what that means. You want to translate? OK. My own, I would like to share with everybody here who is interested in big data analytics. I'm organizing KDD 2014. It will be in New York. It's the oldest data mining conference, kind of academic conference, around for 20 years, and pioneered some of these, the data mining, the notion of data mining competitions. And I would love to talk to whoever's interested in being involved in any way. So please reach out to me. And I have appended in the end some of the references. All of the things I presented are written up in papers. So if you're interested, you can read all the technical details that I didn't have time to present here. Thank you.
OK, so we have time for a few questions.
I have one.
Yeah.
You mentioned that you often have to think about the value of information.
Mm-hmm.
And so I know that there are lots of places you can buy information from that will combine with information that you have. My question is, you didn't talk about using features of any form. You didn't talk about using features of the websites or features of the users. So when you think about the value of information for buying some information about a user, how do you evaluate that? How do you integrate that into your models? Have you got other models that you do use which involve features?
So actually, all my models involve features. There's no such thing as a model without features. But there are these. I have a binary representation, almost like text of URLs. So first of all, these things are already coming in chunks. So of these 100 million, 1 million comes from one data provider, and another 10 million come from somewhere else. So they're already kind of part of the features I buy, and I can decide whether I want to pay for that chunk or not. We have tried to include contextual information that you can buy about the URLs. And on average, they do not provide additional information over what I already know. I don't need it. Same holds for demographic information. We have tried that too. We have tried to include recency and frequency. That didn't work. We tried singular value decomposition and kind of reducing the size of the feature space to something smaller. On average, that doesn't help. So we have pretty much explored most of them. You can buy BlueKai. They will tell you it's a credit card intender. Now, the reality is that's probably a prediction one of their models, which I'm not sure is any better than my model. So that hasn't really yielded, again, marginally over what I already know about browsers. None of the other data sources has really yielded something. So I prefer to work with what I call kind of primary data sources. This person went to this site. I don't care what somebody else predicts this. I don't care what somebody believes the site to be about. I much prefer to have the raw information of what people choose to do. That's the most informative I can get. And that's the stuff we're buying.
Another one?
Just curious, when you're working on these kind of ab initio models and sampling data, how long do you sample before you're able to start creating a preliminary model for discovery?
That's a very good question. So the full model typically runs, the non-streaming models have lookbacks up to 60 days. They start at about 3 or 4 days, but that's actually not important. The important question is, how many positives do I have? And unless I have at least 1,000, nothing really works at all. So the reality is, worst case, it's going to be random. And then I can tell the marketer that I'm working very hard to improve it, and guess what? It will improve in the next week when we get more data. So the key problem typically is to get the pixel up on the marketer's homepage early enough to collect enough positives to be able to build a model. So it's more about the number of positives, and I need a couple of thousands before I can really do anything.
Does that mean that usually sort of like a widely accepted, it's like in your domain, predicting sales, is it the case that usually the baseline is actually random? What is usually the baseline, you know, when you're showing results?
So the baseline is what my competitors can do, in the sense that random actually doesn't mean anything, because if random is a person who doesn't store third-party cookies, nobody can track them. They all perform terrible, not because they don't buy, because nobody knows that they bought. So the notion of random in a world with as much kind of technical layers and complications in the tracking and association is very, very difficult. So typically what people do, they try different strategies, just go by contextual or behavioral advertising, try a blue sky segment, which you can buy, which are credit card intenders, and just see what is the relative performance to each other. Random is really, really hard to define here in this space.
So that would mean that across different companies, they would show just relative comparison of their models, not sort of like an absolute comparison, right?
So the brand who's running the campaigns will not just hire us, but other ones as well, and then they pick the best. On our side, we have a notion of random that we have defined, but if I tell you I have a list of 5, that doesn't tell you anything because you don't know what my random is. So I mean, I can show you these numbers, but I think they're not really, other than internal tracking, they're not useful.
Okay, let's thank Claudia again.